Chapter 8, the Jovian planet systems. So if you remember last time, in Chapter 7, we talked about terrestrial planets. Those were the rocky planets, Mercury, Venus, Earth, of course, Earth and Moon, and Mars. So these are the four rocky objects or Earth-like objects in the inner part of the solar system. But as we move out of the solar system, as we move outward, we come across these giant planets: Jupiter, Saturn, Neptune, Uranus, and Neptune, right? And by the way, Pluto is not one of those, ice giants anymore. So it's not one of the planets, it's dwarf planet, if you remember from last time that we were speaking about it. But we're going to go extensively talk about Jovian planet systems in our solar system. And this is part 1 of the lecture. I've divided the chapter 8 to 2 parts, part 1 and part 2. So let's see what we're going to learn. We're going to learn of what are the Jovian planets made of, what are Jovian planets like on the inside, and what is the weather like in the Jovian planet. So if I'm asking these questions in a homework or in a test, I expect you to be able to answer it, or I want you to be able to answer it by the end of watching this video. So let's take a look at, some of the physical features of these planets. So distance from the sun, from Jupiter, is 5.2 AU. Mass is 318 times of the mass of the Earth. Okay, it's mostly hydrogen and helium. Saturn is about 4 AUs away from Jupiter, so it's standing at 9.54 AU. And if you don't remember what AU is the average separation between Earth and the Sun, about 93 million miles. Okay, and Saturn has a mass of 95 times the mass of the Earth. And then we'll have a huge gap between Saturn and the rest of the planets, Uranus and Neptune. Uranus is standing at 19.2 AU, and it's about 14 times of the mass of the Earth. And Neptune is about 30 AU, and it's about 17 times of the mass of the Earth. They are all having hydrogen and helium, hydrogen compound in their composition. So Jupiter and Saturn are mostly hydrogen and helium, but Uranus and Neptune, they're also hydrogen and helium, but they have water, they have a huge amount of methane and ammonia, and some rocks and some other forms of helium and hydrogen. So beyond the frost line, remember Earth, Mars, Mercury, and Venus form much closer to the sun. Okay, and so as you're much closer to the sun, you are getting more heat, correct? So after that frost line, everything is getting icy. So all of these waters are accumulating, are being accreting on on these dust objects or these dust materials. So beyond the frost line, planetesimals could accumulate ice. That's why we have icy objects in the outer solar system. Hydrogen compounds are more abundant than rock and metal, so Jovian planets got bigger and acquire hydrogen and helium atmosphere. The Jovian core are very, very similar, and they're having similar mass. They're about 10 times of the mass of the Earth. Now, why are they different? Okay, so the Jovian planet differ amount of the hydrogen to helium gas accumulation. Okay, now the question is, why did the amount differ? Why we have this from planet to planet, Jovian planets? Why these amounts are different? We have to consider two things. First, the timing. So the planet that formed earliest captured the most hydrogen and helium gas, The capture stopped after the first solar wind blows and the leftover gas away. So remember, as soon as the nuclear fusion starts in the core of the sun, it creates a huge wind of the charged particle. These charged particles removed everything that was left over from the planet formation. So the location of these formations were the planets that form in the denser part of the nebula form at their core first. Okay. Now let's take a look at the density difference. Very interesting. Jupiter is not the denser. In fact, Saturn and Neptune are denser, even they're denser than Saturn. So Uranus and Neptune are denser because they have less hydrogen to helium ratio. Okay, so in this figure or in this chart, the very important thing is that you can kind of see that Jupiter and Uranus are kind of the same density. Okay. Size of a Jovian planets. Now, don't get fooled. If you're accumulating more stuff, especially more hydrogen, you're not gaining more size. In fact, if I am adding more pillows to this, for example, I am compressing the down layers, the layers below, by further. So that's why if you add more hydrogen or you're accumulating more hydrogen, you're getting less dense. You're getting, you're not getting, bigger, you're getting less and less, but you're getting denser. So adding mass to the Jovian planets compresses the underlying gas layers. Let's take a look at the actual data. So here, what we have is a curve, okay? And the mass of a planet based on the mass of the Jupiter. So in this panel or in this chart, what we have is Jupiter mass being 1, and the radius of the Jupiter is also considered 1. So everything is compared with Jupiter. Saturn, in that matter, is less dense. It's only about 0.3 mass of the Jupiter, okay? But quite surprisingly, it has almost like 0.8 or 0.9 of the mass of the Jupiter, okay? So the greater compression is why Jupiter is not much larger than Saturn, even though it is 3 times more massive, okay? As you're accumulating and gaining more hydrogen, you're not getting bigger because the compression on the down layer will make it smaller, but you're more dense otherwise, right? So Jovian planets with even more mass can be smaller than Jupiter. So if I'm gaining more and more hydrogen, so moving along the X direction, right? I am not going to be bigger in size. In fact, I'm gaining mass, but I'm getting smaller because of the compression. Let's take a look at the interiors of the Jovian planets. So they don't have a solid surface. They're all hydrogen compounds, layers under high pressure and temperature. The core, which is about 10 times of the mass of the Earth, made of hydrogen compounds, metals, and rock. The layers are different for different planets, but we're going to talk about that in a little bit. So let's take a look at Jupiter's, what we have inside Jupiter. So if I'm here in the cloud tops, in the top layer of the Jupiter, as I'm moving down, again, these are all hydrogen. So you don't have a mixture of different materials. It's just different hydrogen phases. We have a gaseous hydrogen on top, and then because of a very high pressure, we have liquid hydrogen. And as you move down, you have a metallic hydrogen. It might be very questionable to you how hydrogen become metal. The reason that we say metallic hydrogen is because they're compressed and they're all very dense that the electron in an atom can move freely from one atom to another atom, okay? That's exactly a property that you expect from a metal, okay? So that's why we call it the metallic hydrogen, because now all the electrons from all the hydrogens are freely moving in the ocean of the materials, okay? As you go further down, you're getting up to the core, which are more metallic, and more rock. The core is probably the size of the Earth, but it's 10 times more massive. Now, if you're looking at the temperature here, as you move from top to the bottom, so about 125 K, and then once you go one layer down to the liquid hydrogen, it goes to 2000 Kelvin. And the pressure is enormous, 500,000 bars, okay? If you're not familiar with this unit, I'll explain that very quickly to you. So bar means this. If I have an area 1 meter by 1 meters, so 1 meter is about 3 feet, so 3 feet by 3 feet, an area like that, okay? And I apply a force of 1 Newton to this area. This is called 1 Pascal. Okay, 1 Pascal. Now, a bar, 1 bar, is 100,000 Pascal. 1 bar is 100,000 Pascal. Okay, so just take a look at this. This is 500,000 bars. This is an enormous amount of pressure. And that's why hydrogen, which is just a proton, right, can have a different features in a liquid form, in a metallic form, and so on and so forth. So the core, as I said, is thought to be made of rocks, metals, and hydrogen compounds, and the core is big enough that is the 10 times of the mass. It's the same size, but it's massive, 10 times of the mass of the Earth. Now, it's very important. I forgot to talk about this. Jupiter is big enough that it has the 71% of mass of all planets combined, and it's about 318 times of the Earth of the mass of the Earth. So comparing Jovian planets' interiors, if you're looking at Saturn and Jupiter, they're pretty much the same. The only difference is that the metallic hydrogen core for Jupiter is bigger. So we have visible clouds on top. We have gaseous hydrogen. We have liquid hydrogen and metallic hydrogen. And then we have the core, which are pretty much similar. On the other hand, Uranus and Neptune, we have visible clouds and gaseous hydrogen, but the core is rocks, metals, water, methane, and ammonia. So pay attention to these. They are similar, but they are also at the same time different size and different densities. So lower pressure inside Uranus and Neptune means no metallic hydrogen. So if you're looking at this, there are no metallic hydrogen as one of the layers. So if I ask you what is the difference between the interiors of Uranus and Neptune compared with Jupiter and Saturn, what I expect to see is that the lower pressure inside Uranus and Neptune means no metallic hydrogen. So that core is missing because it has lower pressure. Jupiter's magnetosphere. So if you remember from our previous chapter, chapter 7, we talked about that we have a huge amount and a huge benefit that we have the magnetosphere on Earth because it is protecting us from solar winds and solar charged particles. It is the exact same thing when it comes to Jupiter. Jupiter has a massive, big magnetosphere protecting it. And it is caused by the interaction of the solar winds particles and Io's particle with magnetosphere. So Io is a moon of or satellite of Jupiter, and we're going to go and talk about this extensively in part 2. So if you're looking at this picture here, I have the Earth magnetosphere magnified 10 times, which is this now. And that is to the scale to what we have for Jupiter. So Jupiter, even though it's that small, it is creating a huge magnetosphere layer of protection. Okay? So all of these particles that are coming from the solar wind, or they're directly coming from the sun, some of them are trapped. Okay, and those are causing the north and south lights on top, North Pole and South Pole of the Jupiter. Now, what is the weather like on Jovian planets? So this is the true color of the, or image of the Jupiter, but this is what Cassini spacecraft sent to us. Okay, let's talk about the weather on these 4 very interesting planets. So Jupiter's atmosphere, we have hydrogen compounds in Jupiter's form clouds. So if you're looking at this, if I consider this being the top cloud or cloud tops on top of the clouds, if I come down, probably somewhere around 35 kilometers down, I have the temperature is cold enough for ammonia to condense and form clouds. So if you see this light greenish clouds, that means that they are formed from ammonia, and they're probably somewhere around 30 to 40 kilometers below the top. Okay, if you're coming further down, probably somewhere around 60 kilometers down, it is cold enough for ammonium hydrosulfide to condense and form clouds. And if you see these red or brownish color, that is ammonium hydrosulfide. If I even come further down, I have this white layer. It is cold enough for water to condense and form clouds. So each color that we see here indicates a different chemical, a different type of cloud with a different depth in the surface of the Jupiter. Okay, so different cloud layers correspond to the freezing points of the different hydrogen compound. This is very, very important. This point is very, very important. Other Jovian planets have similar cloud layers. So light bands, which are like these bands right here, if you're looking at my cursor, are called zone, and darker bands right there are called belts. And we're going to talk about those in a little bit. So bright zones and dark belts. Zones are cooler and are higher than belts. Okay, so if this is the zone, they're brighter, they're higher, they have a low pressure, so they're coming on top. And the belts, which are darker and they're a little bit down, they will go down, the cool material will sink, the warm material will rise. Okay, so Jupiter rotates very quickly. It's about 9.8 hours, so very close to 10 hours. It means high and low pressure regions get drowned into bands. Remember, when you're looking at these bands, it does not mean that they are, one band is moving that direction, the other band is moving this direction on their own. It is due to a very high rotation speed and very high rotation period of Jupiter. It only takes 10 hours to do one complete rotation. Remember, compared to Earth, for us, it's 24 hours. But we are very, very small compared to Jupiter. Now, when it comes to a very big object like Jupiter, rotating that fast, only 10 hours or 9.8 hours, that will cause a high and low pressure regions to get drowned into these bands. They can't escape. So ammonium sulfide, NH4SH, reflect red and brown, what you see here. And ammonia, um, the highest and the coldest layer reflect white. So this is high, this is low. This is exactly what we saw here. All right. Now there are also many short-lived storms on the Jupiter. Again, the color can indicate what depth of the atmosphere we're looking at. Okay, so if I ask you what is the color on the surface of the Jupiter or Jovian planets indicate, you say that it indicates different hydrogen compound. The freezing point of these compounds or these chemicals are different, and it also means that they are in a different depth compared to the top cloud. So I'm gonna show you a video. I'm gonna stop sharing my screen and I'm gonna show a video to you. So let's take a look at this. So I hope you can see this screen now. We'll talk about this green red spot right here, but what I wanted to show you is this. Remember the fast rotation of the Jupiter? It is because of, and this is causing these layers to move, the high and low pressure to move like that. Okay, moving back to our PowerPoint. Let's see, where were we? Right here. Okay, Saturn's colors. Saturn's layers are similar, but are deeper in and further from the sun. So let's take a look at Saturn's atmosphere. So Saturn's atmosphere is similar to Jupiter, except pressure is lower. We have 3 cloud layers, okay, just like what we had on Jupiter. And the cloud layers are thicker than Jupiter's, so it's because we have less gravity and the cloud's less compressed. So if you're looking at this line for Jupiter and this line for Saturn, the Jupiter, the difference between these clouds they're very compressed. They're very close to one another. Compared to what we have on the Saturn, they are further away from one another because Saturn has less gravity. Also, belts and zones are like Jupiter, okay? So if I'm comparing these, I'm looking at the, for example, ammonia cloud, which are looking like a light green. They happen at the same exact temperature, right? But they are further down from the top cloud. So if this is the top cloud layer, they're happening further down from the top cloud. Okay, probably somewhere around 120 kilometers down, versus what we have for Jupiter, it's about 30 to 35 kilometers down. The reason is ammonia clouds form at the similar temperature in Jupiter and Saturn, but deeper in Saturn due to a lower temperature. Okay, remember, if Saturn is about 9 AU away from the sun, versus Jupiter about 5 AU away from the sun. So Jupiter gets more sunlight and it's warmer. So hence we have these ammonia clouds, or any other clouds compared to not only ammonia but ammonium hydrosulfide or water being built in a higher, relatively higher altitude. Saturn's storms are deeper, but the problem is they're harder to see and they don't last as long. By the way, this is the false color, just to enhance the visibility of the bands and clouds. And so these are the storms. This is exactly looking like what we have on Jupiter. Now, gas planets rotate very quickly, as we just talked about Jupiter. Jupiter rotation is about 10 hours, and that causes planet to become flattened or squished. So in other words, if you're looking at this, if let's say this is Jupiter, if you're looking at the North Pole, it is flat. If you're looking at the South Pole, it is flat. The reason is the gravity, which is this green arrow down to the center, it's all the same no matter where we talked about it. No matter what part of the planet we're talking about, it's the same. Okay, oops, sorry. But when it comes to very fast rotation, these pinkish, reddish arrows are different depending where you're located. So the rapid rotation, flings material outward near the equator. So that means it's, squished, it's flattened. In fact, if you're looking at Saturn, because it's moving very fast, the dashed line is a perfect circle, but compare the shape of a Saturn compared to a perfect circle, you can see that it's flattened on top and bottom. And it's due to a very fast rotation. So Jupiter is also flattened, right? 1, rapid rotation of Jupiter, as I said, about 10 hours. 2, no solid surface. And 2 is probably the most important reason why it's doing this, okay? Since it's all hydrogen, it does not have a solid surface, and hydrogen or gas can move more easily. So if I'm comparing the diameter of D1 with D2, I can see that D1 is greater than D2 for Jupiter, and it's about 5,600 miles more. We have the same effect on Earth, but Earth has a solid surface. When it comes to a solid surface, it is harder for it to get flattened. The effect for us is only about 47 miles. When it comes to the Jupiter, it's about 5,600 miles. Jupiter's great red spot. It's one of the most interesting features, or the most visible thing that when you're looking at the surface of the Jupiter will caught your eye and your attention. And let's take a look at that. So a great red spot, or GRS, discovered in 1664 by Robert Hooke, and it's about 22 degrees south of the equator, and it rotates counterclockwise, as you can see in this top picture. So it's moving counterclockwise. So remember, these 2 arrows now indicate the direction of the flow, the gas flow, high pressure and low pressure. And this storm-ish area is trapped between these 2, okay? And it has a period of about 6 days. And you can fit 3 Earths to the GRS, to the Great Red Spot. So it's that big. Now, based on a recent observation, we found that the GRS is moving to the south and it's shrinking over time. So within about a century or so, it'll be gone. But what we know is at least it's 3 to 4 centuries old. Okay, so all Jovian planets have strong winds and storms. Is this only on Jovian planets? Do you remember from chapter 7 that we have strong storms, dust storms on Mars as well? If you remember, I'm very glad, but if you don't remember, go back and read, take a look at the videos on chapter 7, or, take a look at the PowerPoint. But regardless of chapter 7, all the Jovian planets have a strong winds and storms. Methane on Uranus and Neptune, okay? So methane, or CH4, has, a very interesting effect. It absorbs red light, but transmit the blue light. So all of these light, of all the colors comes from the sun. They will hit the surface of the, Uranus, and the methane clouds will absorb the red light and transmit and reflect the blue light. So that's why when you're looking at Uranus and Neptune, you see them bluish or, greenish color. So Uranus in a natural color, it's looking like blue-green. It's because of, as I said, CH4. And is mostly hydrogen and helium, but also water. And, it has more water compared to Jupiter and Saturn. Remember, also Jupiter and Saturn has water, but it's less compared to Uranus. The other very, very, very interesting and important feature of Uranus is that it has a very odd axis tilt. So its axis is tilted 98 degrees, which means it rotates on its side and nearly around its equator. So that will cause a huge seasonal variation on when it comes to the Uranus. Why is that? Why is this? I mean, on Earth we have 23 degrees. We have the same amount of axis tilt for Mars. We have about 7 degrees for Jupiter. But why is that we have 98 degrees for Uranus? The best explanation that we have, and I could find, is that because it had some very catastrophic collision with another planet before. Neptune is also blue. Again, it's because of a methane, a thick methane layer. It absorbs red and reflect blue. Neptune has a storm similar to what we have in Jupiter, but they're fewer. If you're looking at this, time lap in 1996, 98, and 2002, this storm up here is probably gone. Not probably gone. It's gone over years. So stormier means more interior heat. So compared to Jupiter, Neptune is less stormier, so it's less internal heat. So this, as I said, this great dark spot on top has disappeared in the recent years. All right, thought question. Jupiter does not have a large metal core like Earth. So how can it have a magnetic field? Remember, the magnetic field on Earth. So back to chapter 7. Why did we have a magnetic field on Earth? The reason was, if we think, if you're looking at, let's say that this is Earth core. Okay, so let's say this is the Earth core. It is moving pretty fast, right? Hold on. Okay, it's moving pretty fast. It's doing one complete rotation every 24 hours. Okay. Now we have a convection zone in the core, right? So all of these hot materials from the center coming back up, releasing their heat, getting cooler, they're going down. Now imagine that these charged particles going up and down at the same time, rotating pretty fast every 24 hours. This will cause a magnetic field to be created. A moving particle, a moving electron, a moving proton, a moving particle can create a magnetic field. And this is exactly what's happening on Earth, okay? All right, let me clear that. Perfect. Now, Jupiter does not have a large metal core like Earth, and how can it have a metallic or magnetic field? The answer is number 3, uh, part C. It has metallic hydrogen inside, which circulate and makes a magnetic field. So it's exact the same thing as what we see for Earth. So what have you learned from part 1? Jupiter and Saturn are mostly made of hydrogen and helium gas. Uranus and Neptune are mostly made of hydrogen compounds. What are the Jovian planets like in the inside? They have layers with a very high pressure and cores made of rock, metal, and hydrogen compounds. Very high pressure in Jupiter and Saturn can produce metallic hydrogen. Remember, the metallic hydrogen is missing from Neptune and Uranus. What's the weather like in the Jovian planets? Multiple cloud layers determine the color of the Jovian planets and the depth of those clouds. Pay attention to those. They all have storms and very strong winds. So end of part 1. We're gonna go right away to part 2. I'll talk to you guys soon.